In this video, I want to talk about how we can convert between quantum numbers and an electron in a particular orbital for the hydrogen atom. So first off, recall that we have four basic quantum numbers. We have the principal quantum number n, which goes 1, 2, 3, 4, etc. We have the angular momentum quantum number L, which starts at 0 and runs up to n minus 1. And then we have the magnetic quantum number, m sub L, which takes values between negative L, 0, and positive L. So it includes all of L, 2L plus 1 values that span between the negative value in L and the positive value of L. And then finally, we have the spin quantum number, n sub S, which is either 1/2 or negative 1/2. So those are our four quantum numbers. And again, this last one corresponds to spin up or spin down, depending on whether it's positive or negative 1/2. And so if we're talking about filling some orbital energy diagram, for example, we can have something like this. And our general diagram might look something like a 1s, 2s, 2p, 3s, 3p, 3D. I could draw the 4s in here, and as we talked about in some of the main lectures, the 4s is actually slightly below the 3D, but I don't want to worry about those details now. I just want to focus on this sort of bigger picture here. And so if we take, for example, one of these orbits, and I put, for example, an electron right there in that 2p orbital, what are its quantum numbers? Well, the principal quantum number is given by the first letter here, the 1, 2, 3, 4, etc. So for this electron, n is equal to 2. The second, the angular momentum quantum number L, is given by the letter after the number. And so remember, S corresponds to 0, P corresponds to 1, D corresponds to 2. Maybe I should put a 3 in here. And 3 corresponds to F. So in this case, I'm in a p orbit. And so I have L equals 1. Now, m sub L can take any value, in this case, between -1, 0, or 1, because it can range from negative L to positive L. Now, actually, we've talked about how typically we think of these as the 2px, 2py, and 2pz. It turns out that those three orbitals don't directly correspond to m sub L equals -1, 0, or 1. There's some subtleties that are really beyond the scope of this class there. So it's not such a big deal which you call it. Since I put in the middle one, I'm going to call this m sub L equals 0. But in reality, like I say, you have to be a little, there are some subtleties depending on whether you're thinking of these as the raw orbits or the 2px, 2py, and 2pz that we tend to use as chemists more often. But the main point is it's going to be just one of these particular m sub L values, and it's not really a big deal which one. And finally, it's spin up. So therefore, my spin quantum number is plus 1/2. Let's do another example. Suppose I have n equals 3, L equals 2, m sub L equals 1, and m sub S equals -1/2. Where is the electron corresponding to those quantum numbers? Well, n equals 3 means I'm going to be in one of the 3 shells. L equals 2 means I'm in the d orbitals. M sub L equals 1 means I'm in one of those. So I'll go ahead and I'll say it's this one here. And then m sub S equals -1/2 means it's a spin down. So that, for example, would be the electron corresponding to these quantum numbers.